Hello, good morning, evening, and afternoon, everyone. I believe for Brent and I, it's morning. I've got my first cup of coffee ready to go. So I will introduce you to Brent Yorgey. He is an associate professor in the Department of Mathematics Computer Science at Hendrix College in Arkansas, US. Brent has been programming in Haskell for almost 15 years. And over the past 5 years, he's solved over 1,500 competitive programming problems on Open Caddis, and almost thousands of those he's solved in Haskell. Very impressive. He's well known as the author of Type Classopedia, the Diagrams Library, and a certain blog post about burritos. And without further ado, I'll hand it over to Brent.
Welcome. I'm going to talk about competitive programming. So I hope that this talk will be pretty interactive. I'm going to have some things for you to do, actually. I do have the Discord chat open over here on a different screen. So, if you have questions, feel free to just pop them in the chat and I'll be able to see them. And I hope to be able to respond as this goes along. What is competitive programming? So we're going to look at a particular site called Open Caddis. But this is one of many websites, systems in which you can do competitive programming. There's Codeforces, TopCoder, AtCoder. You've probably heard of like Google Code Jam. Maybe if you've done some Advent of Code, you could, that's kind of a form of competitive programming. Open Caddis is one that I happen to like. It hosts the ICPC, the International Collegiate Programming Contest. But there's others, and honestly, actually, some of the most serious competitive programmers in the world, this isn't what they use. They use other things like Codeforces, TopCoder. But anyway, I would say that I'm like an intermediate competitive programmer. I mean, I have an expert rating on Codeforces, which sounds impressive until you realize that there's 6 more levels above that, going all the way up to legendary grandmaster. So anyway, it's something that I enjoy, and in particular, I enjoy trying to solve as many problems as I can in Haskell and pushing the state of the art of what kinds of problems can be solved in Haskell. So what is this about? The thing that these sites all have in common is there's some kind of problems that are specified with very specific inputs and outputs. You said you'll be given some inputs in this format, and you have to write a program to solve this problem and produce some kind of outputs. Typically, you will submit your code, and it will be judged, it'll be run, and on a bunch of secret test data, and it'll be judged whether it's correct or not. Typically, there's a lot of different languages you can use. Obviously, I like to use Haskell, but people use all sorts of languages for these. Sometimes you can do this individually. Sometimes there's team competitions. Usually there's some kind of time pressure, although you can certainly do it sort of what I would say recreational competitive programming where you don't have time pressure. And actually, Caddis is great for that. So you can just pick a problem, work on it, take as long as you want, submit it, and see if you get it right. Okay, I'm going to start by just live coding a solution for you to a very simple problem on Caddis in Haskell, and kind of talk through a little bit of how I solve problems like this in Haskell. So that's how we're going to start. All right, so here is the problem that I'm going to solve. So factorial n, we know what the factorial is. We want to compute the last digit of n factorial in base 10. Okay, which could be kind of interesting, except that actually you see here that n is at most 10. Okay, so we just have to compute, n factorial mod 10 when n is up to 10. So this is not that hard. We can just compute the factorial, do mod 10, and print it out. Okay, okay, there's actually a bunch of test cases. You'll see, right? You get a number that says how many test cases there are, and then each of those next lines contains a number, and then for each of those we have to print out the output. Okay, so I'm gonna leave this open here so you can see it. and I'll explain. Okay, so all right. Okay. So I actually have like this big template that I use, and we're not going to use that because this is a simple problem, and we don't have to worry about that. Okay, so all right, what are we going to do? Well, we're going to write a main because we need to, get some input and print some output. But IO, I don't want to do any IO, and so we're going to use this very nice function that's in the standard library called interact. You may or may not have used this function before, but see, will it show us the type of? So if you look down at the very bottom, I don't know if you can see that, it's very small, but the type of interact says it takes a function from string to string and it returns an IO action. So basically interact we just have to give it a function that processes the input into the output that we want, and it'll handle doing all the actual IO for us. And it does lazy IO, right? So like as it'll demand more IO as our function demands input. So basically all we have to do now, we don't have to do any IO, we just have to write the whole solution as a big function from string to string. So we're just going to transform the input to the output. And I love this way of thinking that Haskell enables. We don't have to think about imperatively looping through stuff. I just have an input and I'm transforming it into the output. Okay. Oh, the bottom of the editor is cropped out. Okay. That's fine. You don't need to see it. Not a big deal. All right. So what are we going to do? Well, what I like to do, typically when I'm doing this, right, I want to think of this pipeline that's transforming the input to the output. And I like to type in the same direction that I'm thinking from beginning to end. And of course, function composition goes the other way. And so if you write it as a big composition of things, you have to write it backwards, which I find kind of annoying in this context. And so what I'm going to do, import control.arrow. I'm just going to import this operator from control arrow that it's basically backwards function composition. And I would never write code in this style, in like serious code for other things, but my coding style when I'm solving problems is very different than my coding style when I'm, working on other projects. So what am I going to do? Well, let's see. I get this input, which is just a big string. Let's first split it up into lines, or we could do words. Actually, either one would work here. So I'm going to split it up into lines. Now I have, a list of these things. And I actually don't care about this first one because it's telling me how many there are, how many other ones there are. But if I'm just getting a list of all of them, I don't need to know how many there are. So I'm just going to drop it. In other situations, you might need that, and we'll probably see a situation like that later. Okay, and then I just want to do the same thing for each of these inputs. So I'm going to map something. Cool. So we're going to do something to each input and transform them into an output. And then, of course, we're going to, eventually do unlines to transform it back into a big string. And so what am I going to do for each thing? I'm going to read it to turn it into an int. I'm going to compute its factorial. And I'm going to, actually, I'm going to split this out into a different function. So I'm going to say map solve. What, in fact, often what I'll do is I'll do like all the processing in kind of, so I'll say like map read solve show. Okay, so solve is actually just working on numbers because conceptually this problem is about transforming numbers into numbers. The reading and showing is just kind of an artifact of the fact that we have to, actually input and output strings. So my solve, I can now say, okay, this is a function from integer to integer. I could also use int. It really doesn't matter in this case. Int is definitely faster if you're worried about speed, but so if I get a number n, I'm just going to say, the factorial or the product of 1 to n mod 10. And that will give me the last digit of the factorial of n. so we can try this out. And I have, so I have a little, oh, you probably can't see that because it's on the bottom. Let me, oops, not that. There we go. All right. I have a little script here called test.py. I'm going to run that, and it's going to. Okay. So it. I have a little Cabal file in here, just like a little template Cabal file. And it ran it on the sample input. So actually, that script I used to create this, you can see that it downloaded these sample inputs and outputs from the website. So these sample inputs and sample outputs here that are on the website, it downloaded those locally. And then when I ran my test, it ran my code on those just to make sure that it worked on those examples. Now, when we actually submit it to Caddis, they have a bunch more secret test cases that they don't show you. So it's possible, certainly, to write a program that works for the examples, but doesn't work for the secret test cases if you missed some corner case or something like that. For this particular example, I'm pretty sure that if it works for the samples, it's going to work. But we can try it. So the way that you can submit, and I'm gonna, let's see, the language is Haskell. I'm going to submit this, and we have to wait for it to run, but it's pretty fast. And it ran it in 4 test cases. The first 2 were probably the sample ones, and then it had 2 more secret ones, and it was accepted. So hooray. So that's the basic idea of how this works. If there are not any questions, then I'm going to actually give you 5 or 7 minutes or so and set you loose on a couple of problems yourself. So here's what we're going to do. I am going to, let's see, how are we going to make this work? Okay. So if you go to this, I have a GitHub repository here. I'm about to push a couple directories which have links to a couple problems that I've selected. One is very easy, and one is, not super easy, but it's not that hard. It's already got like a, it's got all the, it'll have all the test cases in it and everything. You can use that little test.py script. All you have to do is write some Haskell code. What I would encourage you to do, as soon as I push these up, you can clone my repository, try to solve them, and then open a pull request against the repository. And I'll be watching those live. We can see the pull requests come in, and then after 5 or 7 minutes or so, we can kind of look and see what people were able to do. I don't know how reasonable this is. See if you can solve a problem in 5 minutes. But I mean, honestly, the first one, the one is extremely easy. So it's just like a line of Haskell code. So hopefully some people will be able to solve it. And if you can't solve it in 5 or 7 minutes, that's okay. You can keep playing with this later, of course. So I'm going to push these up. I will also push up the example that I just did. Problems, push. So, all right, they're there. So this Autori, this one is the one that is extremely easy. The text encryption is, slightly less easy, but not too hard. So go ahead and clone this repository and give them a try, and then submit a pull request. Yeah, someone asked, they expected the submission to also be scripted. The submission is scripted. I have a script that does that. I didn't choose to do that when I was displaying it here so that people could know how to do it. But
I had a question. So what's in your competitive programming Haskell template that you had briefly shown there?
Yeah, I'll probably show it later. I'm going to do another problem or two, and I'll go over some of what's in there. I mean, I don't have time to talk about everything that's in there, um, I will. I'm happy to make it public afterwards as well, so people can steal from it. Ah, we have some submissions already. I didn't realize I have to actually hit refresh on GitHub to see pull requests. I also forgot that I have to actually like enable the CI to run. I did set up some CI so that it'll automatically run the tests on anyone that submits code. We'll wait another minute and then we'll take a look at what people submitted, and then after that I'm going to go on and try to solve for you live a more difficult problem to show off some of what we can do. All right, well, let's take a look at these three that were submitted. Excellent work. Those of you who submitted something. The CI is not very fast. I don't know how to like optimize CI. It's like downloading GHC and whatever. But anyway, okay, so there's a very simple way to do it. We just filter is upper. Very good. Oh, there's another one. See if anyone did it differently. Okay, so here's someone that basically is looking for writing a recursive thing to go through and look for the dashes and then pick out the characters that happen right after the dashes. I think that will work too. And this is the kind of thing like if you're writing code in a kind of professional setting, you would try to avoid writing directly recursive, Go function like this. You'd use some kind of mapper filter or fold or something. But in this context, if I have an idea for how I want to iterate through a list, I'll often just write the recursive thing directly because it's faster than trying to figure out how I can make it look really nice with a fold. So it's great. Let's see. Okay, so this was done, I think, a similar kind of thing. Okay, we got a few more here. Okay, I can't look at everyone's. Cool. So this one, it's doing something similar, looking for the dashes, but with like a drop while and drop and stuff like that. Cool. All right. Well, I'm not going to look. I can't look at like every single one. And this one failed, I guess. I'm not sure why. All right. Anyway, so let's. So good job. So hopefully that was fun. And obviously you can go. I mean, so if it passed the test, that doesn't mean it will. You have to submit it to Caddis and see if it passes all of the secret tests as well. But you can set up a free Caddis account. You can sign in with Google or whatever you want to do. It's very easy. Definitely recommend playing around with it. But all right, let's move on. So I want to show you. We've got about 15 minutes left, and I picked out a problem that is a little more challenging, and I think shows off some of what's fun about solving these kinds of problems with Haskell. So I'm not going to read the whole thing. I'll kind of just walk through the idea. So basically, we're given some kind of text and a pattern that we want to search for. But the text is not just given as a string, it's described using this kind of grammar, okay? So basically, you can either have terminal symbols like D equals good, that says, okay, the non-terminal symbol D just expands to the text, G-O-O-D. But then we can also have these equations that says, the symbol first expands out to the symbol D followed by the symbol E. the plus here does not mean, it doesn't mean or, it means it's like sequencing. It's concatenation. And so we have a bunch of test cases. Each test case has a bunch of equations. Could have up to 500 of these equations that look like this. And then each equation has some things. But each equation either looks like, something equals something plus something, or it looks like something equals a literal string. And you can tell which is which because these are uppercase and these are lowercase. It specifies that. And then it says, okay, then there's a pattern, and you basically have to see, does the pattern occur as a subsequence of the expanded text? So if you start at the start symbol and you keep expanding things out, you would get some text. And you want to look for the pattern as a subsequence. So it doesn't have to be consecutive. The first character will be somewhere, then you could skip a bunch and then have the second character and so on. The reason this is a little difficult, at first it seems kind of straightforward. You're like, well, I'll just expand this out and then just do a search to the string. The problem is that the string could be extremely long because basically each time you have an equation like this, you can double the length of the resulting string. And if you have 500 of these equations, obviously 2 to the 500th is extremely long. So we have to somehow take advantage of the structure of the grammar to kind of search through it without actually expanding out the entire grammar. So the way we're going to do this is that we want to basically cache some information with each non-terminal. So basically with each non-terminal, we're going to figure out the set of all letters that it can possibly generate eventually. So for example, well, this symbol F, we'll just say it can generate the symbols B, A, and D. Second, in this example, right, it's F followed by E, and so we'll basically just union the set of characters that F generates and the set of characters that E generates, and that will be the set of characters that second can, has. And when we get to a non-terminal, if it can't possibly generate the letter that we're looking for next, then we just skip it. And that turns out to be enough to make this whole thing efficient. So that we don't have to actually keep recursively descending into something if we know that the letter we're looking for can't possibly be there. Let's try this. I don't know, honestly, I'm not sure I'm going to be able to make it through a whole solution in the remaining 10 minutes, but I'll try my best, at least to be able to show you the interesting parts of how I do this. So word equations. Okay. And I can walk a little bit through my, this is kind of the template that I use. And I've got it, I've got these these little foldable things so that Emacs, I can fold them up in Emacs when I want to look at them. But so a whole bunch of language pragmas that I often use, nothing too controversial here, I don't think. A whole bunch of standard library imports. And I've put a little bit of effort into making sure that they don't clash with each other and stuff like that. But I'm not going to go through, probably a lot of these are familiar to you. I will say, right, that you have to know kind of what libraries are installed on whatever judging environment you're submitting to. So on Caddis, they definitely have more than just base. It's basically like, what would come in the Haskell platform. So it includes things like parsec and vector and unordered containers, MTL, but you can't just use arbitrary things from Hackage. You kind of have to stick with what Caddis happens to have installed. So that definitely is restrictive sometimes, but I have this little scanner library. I'm not going to go through the details of this right now, but you're going to see me using it in a minute. And I have a blog post that explains how this works. It's basically just a tiny little parser library, but it doesn't do backtracking, and it doesn't have an alternative instance. because you don't typically need that. And then a whole bunch of utility functions, just things that I find myself using frequently that I like to have defined. All right, so I'm going to define a data type to represent a test case. Okay, in a test case here, it has a number k, which is the number of equations, and it has a bunch of equations. And so I'll just say equations, which is an equation. I'm going to make a data type to represent an equation. So an equation, there's two possible things, right? It can be either let's call it a rule, which has a byte string, okay. The left-hand side, and then the two things on the right-hand side, or it could be we'll call it a terminal, which just has a 2 byte strings. Okay, so this is like a equals b plus c, and this is like a equals blah. Okay, let's see, and then I'm going to make a scanner. So this is this little parser library that I have, and I'm going to say, all right, first we read in, well, right. So instead of just running TC, I'm going to say number of TC. So number of is a function in my little scanner library that says read a number first, and then we're going to expect to see that many copies of the following parser. So number of TC says read a number and then run TC that many times. This is a very, very common pattern in competitive programming where it says the first number tells you how many things they're going to be after that. And then one test case, right, we read in our K, and then we're going to read in, let's see, next scaling equations. Oh, there's like a start symbol. And then, oh, and then there's the pattern, right? Oops, I can't call it pattern, that's a keyword. And then, so we're going to read in K, we're going to say equations, we're going to say K times, we'll make a scanner for an equation. And then, next line is first symbol. Right, so we'll just say pattern, yes. Yes, pattern is a keyword indeed. Okay, so we need our start, which is just a string, and then pattern, which is just a string. And then I'm just using record wildcards here. So like the fact that these things are in scope now that have the right names to go in the record, it'll just package them all up. Which again, I would probably avoid using this in real code, but for doing this kind of competitive programming, works nicely. And yeah, so I'm going to leave this undefined. So I'm really running out of time, and I'm trying to think what, and of course, there's like the Q&A, and we can keep talking in the Q&A, but I want to make sure that I kind of wrap up in some fashion by 10 o'clock, my local time. Let me just kind of tell you, at least give you a sketch of how I would solve this and why I chose this, why I think it's interesting to solve this in Haskell. So ultimately, right, we want to build some kind of map, right, that maps, well, so first of all, of course, we want a map that maps each symbol, so each of these symbols to its equation. That's not hard, right? We read in this list of equations, and then we just like build a map from the left-hand sides to the right-hand sides. But we also want this map that for each symbol gives us the set of letters that it can generate. right? And how do you do that? Well, for these terminal symbols, that's easy because we just literally have, you know, a string here. You know what I'm going to do, actually? That's what I'm going to do. I'm going to just show you the my solution that I already wrote to this, and we can just, I'll just kind of walk through it. Kind of cheating, but it's like a cooking show, right? And we're like, and then we put it in the oven, and then this comes out. So equations. No, make it bigger. Okay. So, well, and you see, I organized the input a little differently in this version, but anyway. So all that stuff up here is just like reading an input. Okay. We can represent a set of which letters are present just using an int, right? And like, you know, bit 0 represents whether there's an A, bit 1 represents whether there's a B, and so on. So rather than actually having a set of letters, that'll make it a little faster if we just use like an int to represent a bit mask. And then this is the key part I wanted to talk about right here. So, right, we need this map that says for each symbol what letters it can possibly generate. But of course, like if we look at a non-terminal like this, well, where first equals D plus E, what letters first can generate, of course, is the union of what letters D can generate and what letters E can generate. And notionally, to compute that set of letters that first can generate, you have to first know what letters D can generate and what letters E can generate. So if you were solving this in like Java, probably what you'd have to do is you'd have to first do a topological sort on the equations, right? By like, set them up, which ones depend on which other ones, and it guarantees it's acyclic. So you can do that. You do a topological sort, and then you do like a dynamic programming thing where you walk through, from the end to the beginning, and you fill in each set where you know that the ones after have already been computed, right? But in Haskell, we don't have to do that because we can just make a lazy map. Okay, so here it is right here. So chars is a map from byte strings to what set of characters that that non-terminal can generate. So it says, right, just go over our equations, and for each equation, just apply this function to figure out what characters can generate. And then char set says, for a primitive, it's just like, all right, it's just these characters in that string. And for a sum, it says, hey, look up what characters A can generate, what characters B can generate, and just OR them together. But right, this chars thing is what we're just defining here. So chars is defined in terms of char set, and char set is defined in terms of chars. So this is a lazy recursive map. And basically, just the laziness takes care of filling it in the right order for us. And we don't even have to do any topological sort or dynamic programming or anything. I mean, I guess this is dynamic programming, but this is what dynamic programming looks like in a lazy language. And then from that, then this like match stuff, this is just like walking through the pattern and looking for each letter, checking whether it's in the character set or not, and doing the right thing. So that's, kind of straightforward in some ways, but this is the interesting part I'm going to talk about. So I think I'm out of time.
Yeah, we're just 1 minute past, but this is very awesome. And you'll be heading to the spatial chat to follow up with any other questions and such like this?
Yep, sounds good. All right, see you all there.
Cool. Thank you. Applause.